Hello. Hi, Catherine. Sorry about that. You missed the first minute. So what I want to do today is I want to go through and talk about the idea of finding the dimension of a subspace when applied to the ideas of the image and kernel of a linear transformation. And we're finally going to prove something that I think some of you sort of noticed a while back, which is that the number of vectors that you need for the basis for the kernel plus the number of vectors you need for a basis for the image are going to add up to something interesting. So, I'm actually skipping page. Which page in the packet is this? 3, 4. 1, 2, 3, 4 in the packet for right now. We're going to come back to it later. I decided I don't want to touch on it quite yet. I'm on page 4 in the packet where we're going to look for a basis for the kernel and the image of this matrix in that particular order. And I know some of you are all sick to death of this by now, saying, Dr. Gerstle, we know how to find the image of a image, and we know how to find the spanning set for the image and the kernel of a linear transformation. Bear with me, we're going to do it one more time in class today, and this time, see if we notice some interesting general patterns. So, here's the matrix we're going to be looking at. 1, 2, 2, negative 5, 6, negative 1, negative 2, negative 1, 1, negative 1, 4, 8, 5, negative 8, 9, 3, 6, 1, 5, negative 7. And today I'd like to start off with finding the kernel of the linear transformation that is multiplying by this matrix. In other words, what does the set of vectors in R5 look like that we could multiply this matrix by in order to produce the 0 vector? So does anybody remember, what's the first thing we want to do with this matrix in order to find a spanning set for the kernel, Henry?
Would you augment it with the 0 vector and then row reduce?
Yeah, we're going to augment with the 0 vector and row reduce, or just in general row reduce. So if we do that, we'll get the row reduced echelon form of A, which we call B today, is going to be the matrix 1, 2, 0, 3, negative 4, 0, 0, 1, negative 4, 5, 0, 0, 0, 0, 0, 0, 0, 0, 0, and of course, 0. So there's the reduced row echelon form. And due to the fact that, as we said way back in Standard 1, row reducing a matrix doesn't change the solution set to any system of linear equations you might set up in using your matrix. We know that if we want to find that the same vectors, x1, x2, x3, x4, x5, that we can multiply B by, the reduced row echelon form by, in order to get the 0 vector, will be the exact same vectors that we should be able to multiply our original matrix by in order to get the 0 vector. Let's see. So if we set up this system and then solve for x1, x2, x3, x4, x5, what I think we're going to get is something along the lines of x1 plus 2x2 plus 3x4 minus 4x5 has to be 0. x3 minus 4x4 plus 5x5 is 0. And because I just know that someone's going to jump on me if I don't write it down, you do get 2 copies of 0 equals 0. So that in order to find the kernel of this linear transformation, we need to find what a spanning set for what does the set of vectors look like that satisfies this system of linear equations. That x1 plus 2x2 plus 3x4 minus 4x5 has to be 0, and x3 minus 4x4 plus 5x5 has to be 0. So, does anybody remember from the last couple standards, what was our strategy for dealing with these equations? Riley?
You rewrite it as like the leading variable equals equals, so it'd be like x1 equals negative 2x2, negative 3x4, plus 4x5.
Yeah, you take the leading variable, the x1, and move everything else over to the other side. And then how about the second line, Riley?
It'd be x3 equals 4x4, negative 5x5.
4x4 minus 5x5. Yep. Don't actually need this equals here. And I'm just going to drop the two 0 equals 0 lines because they're not really telling us anything. So with that, which variables are going to be considered free variables in this problem? No?
2, 4, and 5.
Yeah, x2, x4, and x5. x2, x4, and x5 can be anything, but then x1 and x3 are going to be determined by your choice of x4 and x5. So if we move this over to the sideboard, I want to keep the reduced row echelon form up on the board so I don't have to erase it. We need free variable names for x2, x4, and x5. Ashley, care to do the honors?
Sure. X2 is T, X4 is S, X5 is Z.
I hesitate to use
Oh,
Z
wait,
because Z can oftentimes have meanings
Oh.
implying the third dimension.
I know it makes you squeamish, but G. Did you say that the other day?
I don't. G also gives me apprehensions, but I will allow it this once.
So then x of 1 is negative 2t minus 3s plus 4g, and then x of 3 is 4s minus 5g.
I like it. So if we want to write out what do our vectors look like in the kernel using free variables, x2, x4, x5 are our free variables. X1 and x3 are determined in terms of x2, x4, x5. So how can we use these to then find a basis for the kernel? How can we find, in other words, a linearly independent spanning set for our kernel? Elmer?
You split up the variables, so have t times the vector -2, 1, 0, 0, 0 plus s times -3, 0, 4, 1, 0,
8 digits of pi in there.
and then plus g 4, 0, -5, 0.
Like that. And then those three vectors that we're multiplying by each of our scalars are going to form our basis. Yeah, I like it. So we can say then our basis for the kernel, not kernel of G. Dang it, Ashley, see, got me thinking in terms of functions. Can't do that to me. I'm coming right out of a Calc 1 class where all we're doing is we're talking about like f of x and g of x, etc. It's going to be the set containing -2, 1, 0, 0, 0, -3, 0, 4, 1, 0, and 4, 0, -5, 0, 1. So this is all old hat for you all. You all are pros at this by now because we've been doing this in standard 5. Well, in standard 5 we called it a minimal spanning set. Standard 6 we called it a basis, but been doing this for the last couple standards. With that in mind, here's the new thing. What's the dimension of the kernel going to be? If we're treating the kernel as a subspace of R5, subspace of R5 because all the vectors in the kernel are R5 vectors, what would the dimension of that kernel be, Lynn?
3.
It's 3 because there are, count them, 1, 2, and 3 vectors in there. Yes, Henry?
So, with that, does that imply that there are other sets of vectors, other sets of 3 vectors that form a basis for the kernel?
Sure, I'll show you one. In fact, take any scalar multiples you want of all 3 of these. Any non-zero scalar multiples you want of all 3 of these, and you'll get another basis. Also, as we've kind of seen examples of, you could also form a basis not necessarily by just taking scalar multiples of these 3 things, but by taking linear combinations instead. So if like this is, I don't know, if this is V1, this is V2, this is V3, another way you could have formed a basis is by taking, say, V1 plus V2 minus V3, V1 plus V2 plus V3, 18V1 would have formed a would also form a basis for the kernel. Lots of different bases you could find for the kernel, but according to what we did yesterday, one thing we do know is that any basis you might find is going to have exactly 3 vectors in it. But there's no reason why we need this exact basis specifically for it.
Okay.
Yeah, no?
So, for it to be a basis, it doesn't mean that it has to be, like, I thought part of a basis was that you couldn't make one of the bases as a linear combination. That's not the case.
No, that's true. So in this case, our V1, V2, and V3 are all, not only do these vectors span the kernel, but they also are linearly independent as well. And we talked a little bit about this back in Standard 6, but kind of the reason why we know they're linearly independent without having to actually go through and check is because this is the reduced row echelon form of the matrix. If these were not linearly independent, then we would have been able to row reduce this matrix more. But there's lots of different ways you could choose a basis for the kernel here. Get back to something Henry was saying. But no matter what basis you choose, you're always going to get, or you always should get, that the dimension has to be 3. So geometrically, the kernel in this case would be like a copy of R3 living inside of R5. Try and picture that without your head exploding. So, follow-up question. I'm gonna go back to the reduced row echelon form for a second. I claim that just looking at this reduced row echelon form, I could have told you what the dimension is of the kernel. Why is that? Eleanor?
It's the same number of free variables.
It's the same as the number of free variables. All right, so we had 3 free variables, T, S, and G. What did the number of free variables have to do with the reduced row echelon form? In other words, how could you tell just looking at the reduced row echelon form how many free variables you're going to need? Yes, Eleanor?
How many columns don't have a leading variable?
Yeah, exactly. Because if you notice, the variables out of x1 through x5 that we said we're not going to be considering to be free variables, x1 and x3, those are the columns, well, the first column and the third column that have leading ones in them. So that when we kind of wrote out our system of equations, got x1 plus blah, blah, blah equals 0, and moved everything else over to the other side, we got x1 as an expression of everything else in this top row, x2, x4, and x5. Similarly, in our second row here, we had a leading 1 in our third column, which meant that when we wrote out our system of equations and got x3 minus 4x4 plus 5x5 equals 0, and we solved for x3, the fact that there's a leading 1 here in the third column means that x3 is not going to be a free variable. So that the free variables correspond to the columns without leading 1s in them. Because if you don't have a leading 1 in that column, you're not going to have, like the second column for instance, you're not going to have an x2 equals blah 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 in terms of other variables showing up. So another way you can think about it is the dimension of the kernel is going to be equal to the number of columns in your reduced row echelon form without leading 1s in them. So let's write some of that down. So the dimension of the kernel of A is equal to the number of free variables used to write out vectors in the kernel. Which in turn is going to be equal to the number of columns in the reduced row echelon form of A without leading 1s. So Dr. Gerstle, what's the upshot? The upshot is, if I wanted to just find the dimension of the kernel of our matrix, we didn't actually need to go through the full process of finding the full basis for the kernel. We could have just counted and said, columns 2, 4, and 5 do not have leading 1s in them. That's 3 columns, therefore the dimension of the kernel is 3. Sort of a shortcut method, in other words, for finding what dimension should the kernel of your matrix have. If you know what the reduced row echelon form is, you can just proceed immediately to saying, here's the dimension of your kernel. Any questions or comments related to that? So let's go to image now. Because it's going to turn out there's something similarly interesting that happens for finding the image. So we wanted to find the image of A. Does anybody remember what our procedure was for finding a basis for the image? Me?
Write out all the columns that make A, and then take away the redundant ones.
Yeah, so we said way back in standard 5 that you can find a spanning set for the image by just taking the column vectors of your original matrix, which in this case was 1, -1, 4, 3, 2, -2, 8, 6, 2, -1, 5, 1, -5, 1, -8, 5, and 6, -1, 9, -7. So that's going to give us a spanning set for the image. It's not necessarily a linearly independent spanning set. In fact, I can guarantee it's not linearly independent because we have 5 vectors in R4. And 4 linearly independent vectors in R4 would give us all of R4. So adding a 5th vector is automatically going to make it a linearly dependent set, according to what we talked about in Monday's class. So let's go through our vectors, see which ones are redundant, which ones aren't. Abby, is the first vector redundant? First vector is never redundant unless it's the 0 vector. Abriel, is our second vector redundant?
Yeah,
Why?
it's the first one times 2.
Gadzooks. So yeah, if we call these A1, A2, A3, A4, A5, we can say that A2 is equal to 2 times A1, so A2 already is redundant. It's a scalar multiple of the first vector, therefore we don't need it in finding a basis for the image. How about A3, John?
I don't think it's redundant.
Well, we only have one non-redundant one so far, A1. It doesn't look like A3 is a scalar multiple of A1, so I think we're going to need it. All right, Eleanor, is A4 redundant?
Yes,
It is?
yes.
Can you find me a linear combination of A1 and A3 that'll give us A4?
I know that there should be one, but
Why do you know that there should be one?
because it's a reduced row echelon form.
Hush. We're not looking at the reduced row echelon form yet. So, yes, Eleanor, you are correct. I think this time by just visual inspection, you can't really tell very easily if A4 and A5 are redundant vectors. I think it's relative. A1, of course, is not redundant. Gabriel was able to tell pretty easily that A2 is just 2 times A1, so A2 is not redundant. For John, since we only had one vector we had to compare it to, John was able to tell that A3 is not redundant because it's just not a scalar multiple of the first vector. A4 is a little bit trickier. Is A4 a linear combination of A1 and A3? And we've talked about how we can determine that. Put A1, A3, A4 into a matrix, row reduce the matrix, see if we can find a linear combination of A1 and A3 to get A4 that way. But just from visual inspection, we can't really do that per se. At least I can't. Maybe Eleanor can, but I can't. And similarly with A5, is A5 a linear combination of the previous vectors? Maybe? I don't know, just from looking at it. Unlike with A2, where it was kind of obvious that, yeah, it's just 2 times the first vector, A4 and A5 are kind of trickier, as it usually is once you have to compare it to multiple previous vectors, as opposed to just a single one. So this is a standard 6 question. We would go back and set up and say, a system of equations, can we find coefficients like, I don't know, C1 and C3 that'll make C1 times A1 plus C3 times A3 equal to A4. Set up a system of equations, row reduce a matrix, blah, blah, blah. We're going to talk about a different way to do it in this standard. Because what I want to do in this standard is to talk about how can we use the reduced row echelon form of A to determine which columns in A are redundant columns and which ones in A are not redundant? So we've never actually used the reduced row echelon form to say anything about the image of a linear transformation. We've used it to find a basis for the kernel, or spanning set for the kernel in the past. But we've never really used the reduced row echelon form to find a basis for the image of a linear transformation. Let's talk about how we can do that. All right, Eleanor, why did you say looking at the reduced row echelon form that you thought A4 should be redundant?
Because we have 2 leading variables, so those are the non-redundant variables in the matrix. Because they're ones with zeros everywhere else, so they can't be linear multiples of each other or the other columns.
Yeah. So if you notice something, let's call let's give these columns names in the reduced row echelon form. We're going to call them B1, B2, B3, B4, and B5. And let's see out of B1 through B5, which of those are redundant. So when is if we're looking at these 5 columns, say we're forming a spanning set from them, is B1 going to be a redundant vector?
This is the first one.
first one, it's not the zero vector, so it's not redundant by definition. Ben, is the second column, is B2 going to be redundant?
Yes, because it's just 2 times B1.
Huh. Yeah, so you're saying B2 is equal to 2 times B1. That sounds familiar. Liam, is B3 going to be redundant?
No.
Nope. We only have B1 so far, and it's clearly not a scalar multiple of B1, so it's not redundant. Kevin, is B4 going to be redundant? Once we have B1 and B3. Meaning, is there a linear combination that we can take of the first column and the third column that'll give us the fourth column?
-4b3 plus 3b1.
Yeah, we can say that B4 is equal to 3B1 minus 4B3. So, is B4 redundant then?
Yes.
Very much so. And finally, Abby, is B5 going to be redundant?
Yeah. It'll equal negative 4b1 plus 5b3.
Plus 5B3? Indeed. So B2 is equal to 2B1, just like A2 is equal to 2A1. Oh, that's interesting. B4 is equal to 3B1 minus 4B3, just like, well, I don't know if anything involving A's like that might occur. B5 is equal to negative 4B1 plus 5B3, just like, I don't know. All right, Eleanor, you want to give it another go?
Yeah.
Can you find a linear combination of A1 and A3 that'll give A4?
3A1 minus 4A3.
So you claim this?
Yes.
Let's see, 3 minus 4 times 2 is 3 minus 8 is negative 5. Negative 3 minus 4 times negative 1 is negative 3 plus 4 is 1. And I'll skip the last two calculations because they work out. And it turns out that A4 is equal to 3A1 minus 4A3. Oh, that's interesting. Noel, would you care to guess how you can write A5 as a linear combination of A1 and A3?
-4 times A1 plus 5 times.
I'll check the first couple. Negative 4 plus 5 times 2 is negative 4 plus 10 is 6. Negative 4 times negative 1 is 4, plus 5 times negative 1 is 4 minus 5 is negative 1, etc., etc. Now, turns out A4 and A5 are both redundant. Meaning, what does that tell us about the dimension of the image? Yeah, Peace, Riley.
Yes.
Oh, you're saying it's 2? Yeah, it's 2. Our basis for the image only needs 2 of these vectors, namely A1 and A3. A2, A4, and A5 are redundant, so while this set does give us a spanning set for the image, it's not a basis because you have to remove 3 of the vectors in order to make it linearly independent. So if we crossed out these 3 vectors right here, what's left, A1 and A3, are going to still span the same set that A1 through all of A1 through A5 are going to span, but A1 and A3 make for a linearly independent set. So that would be a basis for the image, which would tell us in turn that the dimension of the image of A is going to be 2. When is that again?
Yeah, so does that mean that like the sum of the image dimension and the kernel dimension will always equal the dimension of the space that they're in?
What do you mean by the dimension of the space they're in? Because keep in mind, the kernel and image live in different spaces. The kernel is consists of vectors in R5, the image consists of vectors in R4 in this case.
Oh, I see.
You're on the right track though.
Okay.
They do add up to something nice. But before we see why, let's go back to reduced row echelon form. Just like I told you all earlier, I could have found the dimension of the kernel just by looking at the reduced row echelon form and looking for columns that didn't have leading ones. How do you think we could find the dimension of the image in a similar way by looking at the reduced row echelon form? Henry?
The number of columns with leading ones.
Yeah, it's going to turn out to be the case that as a general rule of thumb, the dimension of the image of A is going to be equal to the number of columns in reduced row echelon form of A with leading ones. Because the columns that do have leading ones are the ones that we said were non-redundant columns in the looking at and comparing the columns of the reduced row echelon form of A. We said B1 and B3 are not redundant. Those happen to be exactly the columns with the leading ones in them. B2 was 2 times B1, so it wasn't needed. B2 didn't have any leading ones in it. B4 and B5, columns without leading ones in them, and they can also be written in terms of B1 and B3. So as a rule of thumb, the number of columns in your reduced row echelon form with leading ones is going to be the dimension of the image. All right, Gwen, I'm going to revisit your question now.
Okay.
So the dimension of the kernel plus the dimension of the image, according to what we've seen, should be equal to the number of columns in your reduced row echelon form without leading ones plus the number of columns in reduced row echelon form with leading ones. What do you get when you add the number of columns in reduced row echelon form without leading ones to the number of columns with leading ones?
The reduced row echelon form of the matrix.
Well, you get a number, not a
Oh, I
matrix.
see.
Well, if I were to take this number and add it to that number, what would we expect to get? John's making faces. Henry?
Well, if you set m equal to the number of columns of A, then you get the dimension of R and
So in other words, you just get the number of columns of the reduced echelon form, or equivalently, the number of columns of your original matrix. Since every column is either going to have a leading one or not have a leading one. It can't be both of those, and it can't be neither of those. So if you just add up the number of columns without leading ones to the number of columns with leading ones, well, that should just give you the total number of columns. And that, I think, is the observation you were trying to make. So in this case, since the reduced row echelon form of A, or equivalently, the original matrix A had 5 columns to it, the dimension of the kernel plus the dimension of the image of A should add up to 5. So in this case, I forgot to actually put the number down on the board, but it's 2. In this case, we had 5 columns in the original matrix, the dimension of the kernel is 3, the dimension of the image is 2. And so what you just noticed, Wynn, great observation, is that 3 plus 2 is equal to 5. Which I hesitate to say is the dimension of the original space. It's the dimension of the domain of your linear transformation. Because like if you multiply by A, is going to give you a linear transformation from R5 to R4. Because you have to multiply this matrix by a vector with 5 components to it, and you'll get as an output a vector with 4 components to it, since it's a 4 by 5 matrix. But in general, this number plus that number should give you that number. Good observation. Any questions or comments about that? I made me go out of order in my packet, and I was planning on waiting a page before talking about that. Sorry. I'll go ahead and write it up on the board. This is a couple pages later in the packet. We'll come back in a second to the previous pages. Turns out that this is a general theorem called the rank nullity theorem. Which says that for any n by m matrix A, the dimension of the kernel of A plus the dimension of the image of A is equal to m, where m is the number of columns in your matrix. And the proof of that, well, basically, I mean, the proof of this just boils down to this is the number of columns in the reduced row echelon form of A without leading ones. This is the number of columns in reduced row echelon form of A with leading ones. And if you add those together, you're always going to get the number of columns in A. Well, technically you get number of columns in reduced row echelon form of A, but since the reduced row echelon form of A is always going to be a matrix with the same dimensions as your original matrix, REF of A is a 4 by 5 matrix, in this case just like the original A is, that's going to be equal to the number of columns in A. And that is a spanky theorem that gets its own special name. You know a theorem's important in math class pro tip if it has a name to it. It's the rank nullity theorem. Dr. Volsov, isn't the rank nullity theorem awesome?
I like the rank part, I'm not so sure about the nullity though.
Yeah,
That part bothers me.
You're a nullity.
You are in a good mood today, Dr. Kirsten.
Any questions or comments about finding the dimension of the kernel versus the dimension of the image? So in general, if I were to give you an arbitrary matrix and say, hey, tell me what the dimension of the image is, tell me what the dimension of the kernel is, you really all you have to do is row reduce the matrix. Once you have the reduced row echelon form, it's pretty easy to tell. You just count, number of columns with leading ones, that's the dimension of your image. Number of columns without your leading ones, that's the dimension of your kernel. Okay, all right, when you took me off my beaten path, how do I get back on track? So basically the key idea I was going to write down here for the finding the dimension of the image is that the redundant columns in A correspond exactly to the redundant columns in reduced row echelon form of A. So in this case, for the image, if we want to find out of A1, A2, A3, A4, and A5, which of those vectors are redundant, it's not necessarily super easy to tell just from looking at them, as we kind of saw. I mean, it's pretty easy to tell A1 and A3 are not redundant, A2 is redundant, but A4 and A5 were both kind of question marks just from visually inspecting those vectors. Turns out you could ask the same question using the reduced row echelon form of A instead of the original matrix A, and usually looking at the reduced row echelon form of A should be a lot easier to tell which of those columns are redundant, which of those columns are not redundant. The non-redundant ones are the ones with leading ones, the redundant columns are the ones without leading ones to them. So by using the reduced row echelon form of A, you can make it very easy to then go back and look at your original matrix A and say, hey, which of these columns are redundant ones and which ones do I actually need? Just by kind of picking the corresponding columns in reduced row echelon form. Questions or comments? I've got a question then. We said that if we wanted to form a basis for the image of A, gosh, I have a lot of stuff that I want to rip out. Well, that's Calc 1 stuff, I can erase that. We're talking about antiderivatives and indefinite integrals in Calc 1 right now. Spoiler alert, they're all terrible. I don't know why I'm saying spoiler alert, you should have taken Calc 1 in this class. So we have that a basis for the image of A is going to be the set containing A1 and A3, which is the set containing 1, negative 1, 4, 3, and 2, negative 1, 5, 1. So here's a question. We used A1 and A3 to get a basis for the image. Could we have used B1 and B3, meaning the corresponding columns from the reduced row echelon form instead? Meaning, could we have used, 1, 0, 0, 0, and 0, 1, 0, 0 instead for a basis of our image? I tell you what, take a minute, talk to your neighbors, and discuss this over. Meaning, talk to your classmates for a minute, see if you can see what you think. If these would be if this would also serve as a basis for the image just as well, the corresponding columns from the reduced row echelon form, and then when we'll reconvene in just a minute and talk about it together as a class.
Those are very different points.
Feel good about this.
Because the inner spaces is
seems like
where
we're-
there's not a space.
They're both there.
It is tilted.
This is true, they both give you a plane through the origin.
I don't know.
Well, actually, but does it spell
So it's a different.
Oh, yeah, it's not.
A?
It doesn't continue,
Spell.
it doesn't like,
So now.
you can't add A1 and B3 together in a linear combination to get A1.
No.
So they're not the same thing.
Because how would you
So
get zeros
why,
to non-zeros?
Yeah.
why are they one and three?
Yeah, because a basis has to cover like.
Okay.
the-
I guess they have to be.
Yeah, I forgot to say yes, and I feel like I'm not all the way now.
Why not just go zero? Just like a combination of all of them. 0, 0. But there's still, why is it a ratio, right?
Right.
Oh, plane is, 2 vectors, these are any 2 vectors you can have. So they both have a plane, but
Technically, a plane consists of infinitely many vectors, but a two-vector basis.
oh, yeah.
So let's come back together as a class.
They're not the same thing.
Let's put it to a show of thumbs. Thumbs up for we can use it as B1 and B3 as our basis. Thumbs down for we cannot use it as a basis. Seen a lot of thumbs downs. Kevin, Kevin,
Let's just try to be positive.
you know, Kevin, I was about to compliment you for being brave and sticking up against your classmates, but then you changed and I've lost respect for you. I'm just kidding. That's the story. So why not? Why can't we use this set as a basis? I've heard enough from you, Eleanor. I want to get other people in the class. No?
Like you're losing a lot of information just when you get to the reduced row echelon form. Like we're not taking into account the free variables here.
Yeah. So something that's interesting is I think I agree with you. The answer is no, and we can just kind of see looking at these two sets, they don't span the same set of vectors. I mean, if you look at what do these vectors span, it's what's in the span of these vectors, it's all vectors in R4 whose third and fourth coordinates are 0. You take any linear combination of these two vectors, the last two coordinates are going to be 0. Do these look like vectors whose last two coordinates are 0 to you? So I would say, I think I agree with the class. Sorry, Ed. Answer is no. Row reducing your matrix. RREF of A and A have different images from each other. As a general rule of thumb. When you row reduce your matrix, you are going to change the image. Even though, when we do the same thing with the kernel of A is going to be the same as the kernel of the reduced row echelon form of A. In fact, our whole procedure for finding the kernel of A, or finding a basis for the kernel of A at least, is to start by row reducing your matrix. Owing to the fact that when you're finding the kernel, you're finding what vectors can you plug in that'll give you 0 as an output, and row reducing your matrix doesn't change the solution set to a system of linear equations, but it turns out it does change the image of your linear transformation. So the moral of the story is, if you want to find a basis for the image of your linear transformation, or you want to find the dimension of your image, it can still be helpful to find the reduced row echelon form of your matrix A, because knowing what columns are redundant in your reduced row echelon form will tell you which columns are redundant in your original matrix. But you can't then just go and say, oh, B1 and B3 form a basis for the image of A. They do not. You need A1 and A3 to form a basis for the image. Even though using the reduced row echelon form can help you find a basis for the image, you can't use columns from the reduced row echelon form to give you a basis for the image. Any questions or comments related to that? All right, that's going to do it for today then. So when we come back on Friday, actually I have three things I want to do on Friday. First, quiz. Second, little birdie has told me that the course schedule for the spring is going to come out on Friday. And one thing I like to do in all the classes I teach is kind of, once the course schedule comes out, is kind of talk through, hey, here's what's coming up next semester in the math department. Here's what I think make for good follow-up courses to this course, in this case to linear algebra. Just kind of give you some my general feedback on the courses, which we'll spend like 10 minutes or so on. And then after that, we'll talk a little bit more about some consequences of this rank nullity theorem. All right, and with that, have a good day, everybody. Nice job today. I made some really good observations, which I now need to erase quickly before the next class comes in to avoid spoiling them. Take care. Lincoln. Oh.
Thank you.
Lincoln, you can sit down. I tried. There's some big aha moments in class today that I want you to be able to come to on your own. Aha! That's metanoia. Take care.
doing well, that's not a kid.
G for free variable.
Sorry.
No, don't be sorry.
This is the first
I was
letter that came to my mind.
Why the dislike of G?
I dislike G because when I think G, I always think of like a function
Like G of X.
like G of X. Yeah.
So you use it in other classes.
Yes.
No,
That-
this-
to be fair, there is nothing mathematically wrong with using G
Right,
there.
right.
It's just that certain letters have certain you have immediate like things that they make you think of.
Yeah.
Usually when you think of free variables, you're thinking of like R's and S's and T's. When you use F and G, I'm used to thinking boom function. X, Y, and Z, I'm used to thinking boom coordinate names of.
There you go.
I heard Gödel's incompleteness theorems explained with variable G, so I think of a self-referential statement.
Okay, here's the difference. I don't usually teach Gödel's incompleteness theorem. That's Dr. Giggler's domain.
Well, I mean, that wasn't here, I don't think Gödel actually used G for it, but
I don't know what Gödel would have used.
explained it that way.
I was gonna say I've never seen it phrased in like Gödel's original writing. So.
Yeah.
All right, let's erase some of this. Oh, I forgot to turn off video.